Hi students, in this class we are going to study the phenomenon called corona in the transmission line. During the normal working condition, the air surrounding the transmission line consists of ionized particles. When the potential gradient on the conductor surface reaches some 30 kilovolt per centimeter, the velocity acquired by these free ions will be sufficient to collide with the neutral molecules to release electrons from them, and these electrons will collide with another molecule to release more number of electrons. This is a cumulative process. Finally, it leads to the formation of a violet glow along the length of the transmission line. This is called corona. The phenomenon of violet glow, hissing noise, and the production of ozone gas in an overhead transmission line is called corona. There are certain factors which affect the corona formation. The first one is atmospheric condition. If it is a stormy weather condition, then more number of ionized particles will be present surrounding the transmission line. So the corona occurs even at a lesser voltage. Then it depends on the size and the shape of the conductor. If the conductor has an irregular shape, then the potential gradient will be more on the conductor surface. The corona occurs even at a lesser voltage. Corona basically depends on the potential gradient on the conductor surface. Gradient is directly proportional to voltage and is inversely proportional to the spacing between the two conductors. So when the spacing is less, the gradient is more, corona occurs very easily. If the voltage is more, the gradient is more, then the corona occurs very easily. There are certain advantages with the corona formation. As you know, when the corona is formed, surrounding the transmission line we have ionized particles. So the virtual diameter of the conductor is increased. The corona reduces the effects of transients, especially the transients from the lightning strokes. Some disadvantages with the corona are: the first one is it is accompanied by the loss of energy, because when the corona is formed, as you know, violet glow is formed. So the light energy is there, then heat energy is there. It produces a hissing noise. The sound energy is there. Then some chemical reactions occur there, due to which the ozone gas is formed. So for all this process, the energy is necessary. That's how the loss of energy comes there. Then the production of ozone may cause the corrosion of conductors. Then the currents drawn by the line due to the corona is non-sinusoidal, so which will produce the harmonics in the system. Let's see the term potential gradient. Gradient G is equal to V divided by R into log D by R. Volt per centimeter, or it is kilovolt per centimeter. When the potential gradient on the conductor surface increases, the ionization of the air surrounding the conductor material occurs. The potential gradient at which the complete disruption of air occurs is called disruptive strength or the dielectric strength. The dielectric strength of air is 30 kilovolt per centimeter. This is the peak value. If you want to find out the RMS value, it is 30 divided by root 2, which is equal to 21.1 kV per centimeter. This is the RMS value. This is the dielectric strength of air. We'll see a couple of terms related with the corona formation. One is critical disruptive voltage. This is the minimum phase to neutral voltage at which the corona starts. So this can be calculated from the potential gradient. As you know, G equals V divided by R into log D by R. So from this, V equals G R into, it is logarithm to the base E, D by R. So this is critical disruptive voltage. So this is G0, the dielectric strength of air, or it is the gradient. Actually, this gradient is for the standard atmospheric condition. This is for 76 mm of Hg and 25 degrees centigrade. If you want to find out the critical disruptive voltage at the atmospheric condition other than the standard values, then the Vc becomes delta into, where delta is called air density factor, G0 R log D by R. If G0 is in kilovolt, this is also in kilovolt. Delta is air density factor. This is air density factor. Delta is equal to 3.92 B divided by 273 plus T. Here B is the barometric pressure in centimeter of mercury, and T is the temperature in degrees centigrade. So we can find out the critical disruptive voltage at any atmospheric condition, but you need to include the term the air density factor corresponding to the particular atmospheric pressure and the temperature. Now we need to consider the surface condition also. Considering the surface condition of the conductor, Vc becomes, there is a term M0 into delta G0 R log D by R kilovolt. Where this M0 is called irregularity factor. This is irregularity factor. This is equal to 1 for polished conductor, and M0 equals 0.98 to 0.92 for dirty conductor. So using this formula, we can find out the critical disruptive voltage. Vc equals M0 delta G0 R into log D by R. There is another term, visual critical voltage. This is the minimum phase to neutral voltage at which the corona glow appears. Appears all along the line. That's why we call it visual critical voltage. Or VV equals MV, which is the roughness factor, into G0, that's the dielectric strength of air or the gradient, delta R into 1 plus 0.3 divided by square root of delta R into log D by R, kilovolt, where this MV is the roughness factor and this is equal to 1 for polished conductor and this is equal to 0.72 to 0.82 for rough conductors. So using this formula we can find out the visual critical voltage. Now we find out the power loss under the fair weather condition, under the good weather condition, using the Peake's formula. Where P equals 242.2 into F plus 25 divided by delta into root of R divided by D into V minus Vc the whole square into 10 raised to minus 5 kilowatt per kilometer per phase. Here V is the phase to neutral voltage, is the RMS value, and Vc is the critical disruptive voltage. Vc is the critical disruptive voltage. This is also in RMS value. And D is the spacing, where R is the radius, where delta is the air density factor. F is the frequency. So using this formula we can find out the power loss under the fair weather condition. We can find out the power loss under the foul weather condition or under the stormy weather condition using the formula P equals 242.2 into F plus 25 divided by delta into square root of, this is delta, the square root of R divided by D into V minus, there is a slight difference in the formula, it is 0.8 Vc, where Vc is the critical disruptive voltage at the normal working condition. Under the stormy weather condition, the disruption occurs at 80% of normal voltage. So it is 0.8 Vc. Disruption occurs at a lesser voltage. That's why we are substituting 0.8 Vc instead of Vc. The whole square into 10 raised to minus 5 kilowatt per kilometer per phase. All other parameters are same. So using this formula we can find out the power loss under the stormy weather condition.